Okay, welcome back. When we left off last time, I had asked you to answer the questions on this page, so we'll go over them. What are the three ways that heat can be transferred? Combustion, which is direct contact, particle to particle. Convection, where the heat moves in a current. And basically what's happening, the heated liquid or gas gets less dense and it rises. As it rises, it begins to cool and becomes more dense and it sinks. So there's this constant process of rising and sinking, and then it starts swirling. Radiation is the heat transfer where it moves in electromagnetic waves. It's important to remember that the first two require matter because you have to have particles, you have to have a substance for the heat to move particle to particle in direct contact. And of course, if there's going to be a convection current, you need either a liquid or a gas, so you have to have matter. Radiation can move to a vacuum and no matter is required. Okay, what's the difference between an insulator and a conductor? Well, insulators slow the movement of heat and conductors allow the easy movement of heat. And what two things make the best insulator? Gases, vacuums, and reflective surfaces make the best insulators. Gases and vacuums, gases stop conduction, and if you have them trapped, like with insulation inside of a wall, they also stop convection. Vacuums stop both convection and conduction, and then reflective surfaces stop radiation. What is cold described in scientific terms? We didn't describe cold in scientific terms. There is no such thing as cold in science. Cold is just merely the absence of heat. Remember, we can measure how much heat is in something. We can measure the energy of the particles, but we cannot measure cold or the missing energy. Okay. In this unit on heat, of course, heat is what causes phase change. So this is a review from things that we learned in the first semester. Okay. Physical change of matter to another is called a phase change or a change of state. And matter will change state if we add enough thermal energy is either absorbed or released. So we can either be heating it and it's absorbing energy, or it can be releasing energy. Okay, just a review of this phase change graph down here at the coldest temperatures, we have a solid. The solid warms, it melts and becomes a liquid. The liquid heats, it boils and becomes a gas. So we have our three phases of matter here, solid, liquid, and gas. Along the lines that are flat, we have phase changes, which if we're adding energy would be melting. And if we were releasing energy, it would be freezing. And up here, when the liquid finally heats, okay, the phase change is either vaporization, where it's turning to a gas, or if we were cooling it, when a gas turns back to a liquid, it would be condensation. Okay. During phase change, remember that the temperature stays constant. Both melting and freezing happen at the same temperature, and during freezing or melting, the temperature remains constant. It's either forming, the energy is either going into forming the bonds to make a solid from a liquid, or it's going into breaking those bonds so that it can turn from a solid to a liquid. Okay. Phase change remains, the temperature remains constant during boiling. This is why we can refer to something and say the water boils at 100 degrees, or in Fahrenheit, it boils at 212. And it stays at that temperature during the entire time it's boiling, because again, the energy that's being added to the liquid, instead of it making the particles move faster and having the temperature go up, the particles have reached that fastest place. The bonds aren't strong enough to hold them, so when they try and move faster, the bonds break. So the energy that's being added during this time is going to breaking bonds. The name of the energy that's being added during or removed during either melting or freezing is called the heat of fusion. And the energy that's being added during vaporization or removed during condensation is called the heat of vaporization. Okay, phase change, solid to a liquid. Melting is when a solid, like ice, turns into a liquid, like water. Freezing is when a liquid, like water, changes into a solid, like ice. Vaporization is when a liquid changes into a gas. Condensation or condensing is when a gas changes back into a liquid. Okay. Evaporation is a liquid changing into a gas. This happens only at the surface and requires less thermal energy. So like when you sweat and there's moisture on your skin and it evaporates, it takes with it the heat of vaporization, but it doesn't do it all at once. It's happening only at the surface. And if you think like water in the ocean, when it evaporates from the top. It doesn't evaporate from the bottom of the ocean. Okay, I want to take a look at this clip on change of state. It uses using heat. Okay, so part of this unit is for you to understand the different way homes are heated. As you become a young adult and go out into the marketplace, hopefully you'll be looking for a place to live. And it's important to know the advantages and disadvantages of different kinds of heating systems that may be in the home. So heating systems are used to warm homes and buildings. Okay. The first kind of system is called forced air. So its name describes exactly what it does. Air is forced. It's forced to move. Okay, so a fuel source heats the air, and then the air is blown through ducts or vents. That's the forcing part. There's a fan that pushes the air out. Cool air is then returned to the furnace to be reheated. Okay. Conduction heats the air when it's in the furnace, and then convection transfers the warm air to parts of the building. Okay. A forced air system, okay, has a vent. This is where the air is forced out by the fan from the furnace. So if you see one of these in your home, a lot of times they're along near the floor. Okay, so that it lets the air out. Someplace in the room, there's a place where the air has to be returned. So if you think about it, the air can't just blow and blow and blow into the room like the house is a big balloon. It has to go back someplace to the big fan that's called an air handler, a heat pump or a furnace or however the air is heated. It has to recycle back. The next kind of system is called a radiator, and it does exactly what it says. It radiates energy. The air is heated through radiation or conduction as the air touches the hot radiator, and then convection currents move the warm air around the building. Okay, so we took a look at this when we looked at convection currents, but here it is again. So in this kind of radiator system, there's hot water, and it shows here someplace in your home would be a place where there would be some kind of a burner. Usually these are natural gas or heating oil, and it heats up the water, and then the hot water is pumped, and then these things are along the baseboard, and I'll show you a picture of what they look like. Basically, they get hot, they heat the air around them, and then the air rises and cools and creates convection currents in the room, and this is how it circulates around the room. Okay, this is what this thing that's along the baseboard with all these metal, they're called fins, okay, where the air is, they're usually covered like this. So you can see right here where my cursor is, that's where the pipe of the hot water comes up out of the floor, and then it runs through here. The metal gets hot, the convection current, the air rises up through this opening, and then it circulates around the room. Here's kind of a cutaway where you can see this copper pipe that'll carry the hot water behind this thing to heat those metal fins up. And here's actually a little bit more cutaway. The copper pipe is going in. These little pieces of aluminum get really hot. The air around them warms up. Hot air rises and makes a convection current in the room. In really old homes or old buildings, they have these even more old-fashioned radiators. They work exactly the same way. You can see this water pipe comes up, goes in here with hot water, heats this thing up, and then it radiates and transfers energy into the room, creates convection currents. And the last one is an electrical system. Okay, electricity is heated. Okay, transfers energy by radiation and conduction. Convection moves the air around the home. Okay, the most common system is the forced air system. And then the radiator systems are very effective. They're mostly in older homes. They're expensive to install because you need a second set of plumbing to put all those things along the baseboards. And then the electrical systems, you know, as you become a new homeowner, those are the ones you should stay away from. They're the house is heated strictly by electricity. They're inexpensive to install, but very expensive to use. Okay? And the electrical systems work by getting this one is not a whole house system, but it shows there's a piece of metal in here and the electricity runs through it. It's called electrical resistance. So it's just friction is the electricity goes through the metal, and the friction, just like, you know, anything that rubs together, when the electrons rub through the metal, makes the metal really hot, and then the hot metal glows, and that's what heats the room. Okay, it works the same way as a burner on a stove. The electricity goes in here, and the resistance or the electrical friction makes this thing hot. Okay, and instead of just being a burner on a stove, it's used to heat the whole home. Sometimes they have small ones like this in bathrooms, and when you turn this on, the electricity goes through these little wires that look like springs, and they get really, really hot. And usually there's a fan behind them sometimes to blow the air around. Another way people heat their homes is using solar heating, okay, and it uses energy from the sun to warm an area. And there's really two ways that solar heating works. First one is called passive, and passive solar heating doesn't use any mechanical devices. Okay, so just like hot air, the sun shines through a window, and it heats the house. Okay, so when it says passive, it means like you haven't built anything or done anything special, or, you know, passive is like this way you face the house so that you get sun during the daytime. And active solar heating actually uses some kind of a solar collector. That's why it's called active, because you actually did something. You installed solar collections to absorb the radiation energy, and they circulate that energy in the building. This is an example of an active solar system. This one's used to heat hot water. Sometimes it can be used to heat the home. They all work pretty much the same way. So what it shows is the cold water goes up, and then these a lot of times are made out of like thin vinyl or thin plastic, and there's a whole bunch of little pipes that go back and forth, back and forth, back and forth, back and forth. And usually they're black on the roof, so they get really hot. So as the water travels through these little tubes in here, it gets hot because, you know, the vinyl or the plastic is heating up. And by the time it gets to the other side, it's really, really hot. And then it goes back to the hot water heater. And so, you know, if this is an electric hot water heater and the water comes in and it's already pretty hot, then it doesn't require very much extra electricity to supply the house with really hot water. So, and then usually there's a pump someplace that pumps the water up here when more hot water is needed, and it goes through these panels. When I was a kid, we had one that was very similar to this, but it heated the water in the swimming pool. So the water from the pool came up, went to these panels on the roof like this, and went back to this swimming pool, and it kept the pool nice and warm. Okay, now people use heat to turn heat into mechanical energy. So a heat engine is an engine that converts thermal energy into mechanical energy. Combustion is the process of burning something. So the combustion is what makes the heat, and then it makes the thermal energy, and then the thermal energy is going to be turned into mechanical energy. First kind of engine is the most common one. It's called internal combustion. Internal means inside, so the fuel's burned inside the engine or chambers of the cylinders. An example is most cars, buses, lawn mowers, pretty much anything that burns gasoline and has an engine or a motor in it. They convert about 20% of the chemical energy in the fuel into usable energy of motion. Okay. Here's an example of an internal combustion engine. Usually they're called four-stroke engines because there's 4 times that the piston will go up and down. So in this first one, it says this is the intake stroke. And this is where the engine kind of inhales, just like you inhale. And so you can see that on this one, there's 2 valves at the top. And this one is open. So the air and the fuel come in, and the piston is up at the top, and it pulls down, and it sucks in fresh gas and air. Now, the piston is down at the bottom. So if the spark plug went off now, nothing would happen because the piston's already at the bottom of the cylinder. So the next stroke that happens is the piston goes back up, both of the valves are closed, and it squeezes the gas and air into a really small space. That's called compression. And last year we learned that chemical reactions usually don't happen on their own. So the spark plug provides activation energy and starts an explosion. The gas and the air burn. The explosion, the piston's up at the top from the compression stroke. The explosion happens, okay, and it forces the piston down. And that's the third stroke, which is the power stroke. Now the piston's down at the bottom. The cylinder is filled with the burnt gas and air. The other side valve opens up, the piston goes back up, and it pushes out the burnt gas and air, and that's the exhaust. Then it happens again, piston is at the top, it pushes the gas and air out. Okay, the other valve opens up, piston goes back down, sucks in fresh gas and air. Both valves close, it goes up and it squeezes it and compresses it. Then there's the explosion. Both valves stay closed, the piston powers down, and then the other valve opens up and it exhales and there's exhaust. And so over here is a little moving diagram of a 4-stroke engine. You can see on each cylinder, the one valve, the blue one, will open up and new fresh gas and air come in. Then the piston goes up and it squeezes and there's an explosion. And then the gas is burnt and it goes out the other side as exhaust. So when you look at like a tachometer on a car and it says the engine is going 2,500 revolutions per minute, that means it's spinning around 2,500 times per minute. So in this case, is a 4-cylinder engine. So the engine's going around 2,500 times per minute. And there's 4 cylinders. That means there's 10,000 little explosions per minute because there's 4 cylinders. So 4 times 2,500. The next kind of engine is called an external combustion engine. And this means the fuel is burned outside. External. That's, we have internal means inside, external means outside. And a steam engine is a good example of this kind of engine. So the fuel's burned outside the engine. Over here is the piston, and that's what moves the wheels. So this is, like if this was a internal combustion engine, this is where the gas and the explosion happened. But there's no burning going on in here. The burning and the combustion is done outside the engine over here, and it heats up this water and will make steam and goes over here, and the high pressure steam is what pushes this piston back and forth. So the burning is over here. It's external to the engine. The engine is where the piston is. In the internal combustion engine, the difference is the fuel is burned inside the cylinder. It's inside the piston right here. So as opposed to this, which just has the steam in it. So an example of the way it works is externally over here, the water is burned and it makes this steam, and the steam goes over to the engine, and then the steam is represented by the red, and so it goes on one side of the piston and pushes it back, and then on the other side of the piston pushes it forward, and then back and forward, back and forward. So the burning is done externally, and this is how, when you see a picture of an old locomotive, or you go to amusement park that has one, this is what's happening. there's no burning going on inside this engine over here, inside where the cylinder is. The burning is done outside of that, and then the piston pushing back and forth pushes the wheels, and that's what makes them turn. Okay, we're gonna stop here and pick up with heat movers next time.